This is my 8-bit homebrew CPU. In the previous episode, I've added an instruction decoder, which now allows me to have much more fancy instructions execute on the CPU. This here is an example program that we've been using to test the CPU. It uses a loop to compute the numbers in the Fibonacci series by adding up the previous two Fibonacci numbers. And once this addition overflows, which means we've reached the largest number we can compute, we break out of this loop and then finish the program. And this combination of a conditional load immediate and a jump relative with register here is how we've been doing conditional jumps. We first load register R6 with the jump offset that's needed to continue the loop. And then we use a conditional load immediate on carry to override this jump offset with the value 2 in case the carry flag is set, which means we've reached the largest number. And then we use the value in R6 to perform a relative jump. This is a bit annoying because we're wasting a register to hold this jump offset, and we also need two instructions to perform this conditional jump. But most of the time in practice, you want to conditionally jump by an immediate offset. You want to take the flags, check if some condition holds, and then jump a little bit forward or backwards in the program. Let's go and add that to my CPU. Let's build a functional unit that can control these jumps and conditional branches. For that, we'll need a way to check if the current flags in the CPU match a certain condition. We're already doing this on the ALU PCB to implement the conditional moves and conditional load immediates, so let's go build a small PCB that just contains that circuitry. This is the schematic of the ALU that we've built, and I think I want to just copy the condition matching circuitry that's already on here. Then let me add a header for the condition code. And we need a header for power and the condition match result. Okay, that's all the connections we need. Let me create a PCB for this. Let me copy some of the stuff over from the ALU PCB because we've already laid it out there. And then let me arrange the pin headers at the bottom so it's easy to plug this into a breadboard. Clean up things a little bit, and then make the missing connections. Alright, pretty sweet. That's a nice little compact PCB. Let me build this up and then let's see if we can make use of this in a branch unit. I just got this back in the mail. Let me quickly clean stuff up with isopropyl alcohol and then apply some solder paste to one of the PCBs. I definitely have to get new solder paste pretty soon. This one is all dried up. Then let me add the components. There are 3 100 nanofarad capacitors. Then we have a 15 kilo ohm resistor for the LED. And then the green LED itself. Then we have a tiny chip with two 2-input OR gates. There's just the tiniest dot on that package, so you know which pin is pin 1. Very hard to see though. Then we have a chip with 4 2-input XOR gates. And finally an 8-input multiplexer. Alright, that looks pretty good. Let me fire up the hot air gun and solder this up. Then let's add the pin headers. Okay, that looks pretty good. Let me give this a quick cleanup off camera and then let's add this to the CPU build. Alright, I got the CPU back out, and if I power this up and hit run, It's going to clear out the register stack and then compute the largest 16-bit Fibonacci number. Seems to be still working, so that's a pretty good starting point. The program counter, which sits up here, has two mode select input bits. These control whether we step to the next instruction or we do a relative or absolute jump. And these two control signals are currently directly connected to the first decoder ROM. But now that we have this handy condition matching circuit, we can be a bit more clever about how we set these control lines. Let me add this to the decoder breadboard. Down here in the bottom left, looks like we have some spare space available. To control the program counter more carefully, I think I want to add a branch unit, a new kind of functional unit to the CPU. We currently have the move unit, which is unit 0, and the ALU, which is unit 1. So I think we'll make unit 2 the branch unit. Let me add an LED such that we know when the branch unit is selected. And then let me connect that LED to output number 2 of the demultiplexer to make this the functional unit 2. So we now have an active low control line which enables the branch unit. Let's quickly think about how the branch unit should behave and how it should affect the program counter. If the branch unit is disabled, we simply want to step to the next instruction. This means we're sending mode 0 to the program counter, regardless of what the condition matcher says and what the decoder provides as a jump mode input. If the branch unit is enabled but the condition does not match, we also just want to step to the next instruction. However, when the branch unit is enabled and the condition does match, we want to take the mode selection from the decoder and forward it to the program counter. If we get the mode 0-1, a relative jump from the decoder, we want to forward this to the program counter. Same goes for an absolute jump, mode 1-0. Basically, we just forward the mode selection from the decoder to the program counter. So let's think about how we can compute this mode output that we send to the program counter. Let's start with the lower bits. And let's take a look at where the 1s are. This looks pretty straightforward. There are only two cases where we have to produce a 1, and they are basically identical. We produce a 1 if the branch enable is set, the condition match is set, and the mode input bit 0 is set. And we can just take these signals and shove them into a 3-input AND gate. And then similarly for the other bit of the output mode, there are two 1s we need to produce, and they're basically identical. And this is a pretty common pattern. If you want to override a value to 0, you would use an AND gate. This is our input mode. We want to override it to 0, so we use an AND gate. Or if you want to override a value to a 1, you can use an OR gate. Now, this branch enable down here is problematic because this is an active high signal, but on the breadboard, the branch enable we have is active low. So we need to invert this somehow. Ideally, we don't want a dedicated inverter chip to do this. So let's apply De Morgan's rule. We can invert all the inputs and turn the AND gate into a NOR gate, and this still performs the exact same computation. This is pretty nice because this inverter branch enable signal we do have on the breadboard. However, now we have this inverter condition match signal, which we don't have on the breadboard. But since we're already using NOR gates, we can just use another NOR gate to invert the condition match signal that we do have. And then we have this mode input signal that we need to invert. Since this comes straight from the decoder, we can just make the decoder emit the inverted version directly, so we don't need additional inverter gates on the breadboards. And all we need to implement these conditional jumps are three 3-input NOR gates. I'm going to use a 74HC27, which is a chip with three 3-input NOR gates. Let me hook up power and ground. I'm going to use one of the NOR gates to invert the condition match signal. This now produces the inverted condition match over here at pin 12. On the remaining two NOR gates, we're going to connect one of the inputs to the jump mode bit. This is going to be one of the bits coming out of the second decoder as an opcode for the branch functional unit. I'm just going to connect those to 1 for now. Another input of the NOR gates will connect to this inverted condition match signal. And the third input to the NOR gates we will connect to the branch enable signal. And the outputs of these two NOR gates we can now directly connect to the program counter's select inputs. So the branch unit now takes the enable signal, the desired jump mode that will come from the decoder, the condition match result, and it will produce the select control signals for the program counter. Let's quickly check if this works as expected. I'm going to set the branch enable signal to 1 to disable the branch unit to get started, and the condition match signal I'm going to set to 0. I'm going to ignore the rest of the CPU for now. So when the branch enable signal is inactive, the branch unit is not enabled, the LED is off, and the program counter is in stepping mode. That is, the select inputs are set to 0. And since the branch unit is not enabled, even if I toggle the condition match input, nothing happens. And even if I set the jump mode and the condition match signals to a value that would trigger a jump, nothing happens because the branch unit is not enabled. Let me activate the branch enable line, which now turns on the LED indicating that the branch unit is selected. But since the condition match signal is 0, the mode select of the program counter is still at 0 in stepping mode. And so if this were a conditional jump and we wouldn't see a condition match, so we wouldn't want to jump, this is the correct behavior. We would want to have the program counter just step over the jump to the next instruction in that case. But when I now set the condition match signal high, the select input of the program counter is no longer 0. In fact, I can change the jump mode inputs to the branch unit and they will show up as select inputs at the program counter. Because we're using a NOR gate, these are actually inverted. So whenever the branch unit is enabled and the condition match signal is high, the select lines of the program counter are going to be set to the inverse of the jump mode. So because of this inversion, if we set the jump mode to the value 1, 1, we get the program counter mode 0, which is stepping mode. If we set it to 1, 0, we get the program counter mode 1, which is the relative jump mode. And when we set it to 0, 1, we get the program counter mode 2, which is the absolute jump mode. And if we set it to all zeros, we get this reserved unimplemented mode 3 of the program counter, which currently just resets it to 0. And whenever the condition here did not match, the program counter input will go back to 0, just stepping mode. And the same if the branch unit is not selected. The program counter will just be in stepping mode, which is the default for all instructions except for jumps. Now, instead of manually controlling this condition match signal, let me connect the new condition matcher PCB to power, and then let's take the condition match from its output. If you remember from the ALU build, we have quite a few condition codes available that this condition match circuit can check. I've currently connected the condition input to 0, which is the always condition that will always match. Correspondingly, the match LED goes on, and the branch unit is forwarding the jump mode to the program counter. If I set the condition input to 1, which is the never condition, the condition match LED turns off, and the program counter goes back into stepping mode. But we can also check the flags. For example, I can set the condition code to the value 2, which is the condition flag check, which results in a 0 because the carry flag is not set. But if I turn the carry flag on, you can see that the condition matches again, and the program counter again goes into jumping mode. And then we also have the inverted versions. If I select condition code 3, which is the not carry condition code, you can see that the condition match turns off and the program counter goes back into stepping mode, not taking a jump because the carry flag is set. And when I clear the carry flag, the condition match goes on again and the program counter is back to jumping mode. Most instructions will not use the branch unit, so the branch unit will be disabled for most of them, which means that for almost all instructions, the program counter is going to be in stepping mode, just advancing to the next instruction and not jumping around. For all our jump and branch instructions, however, we will select functional unit 2, which is the branch unit. And the decoder can then set the jump mode signals here to control whether the program counter should do a relative jump or an absolute jump. On top of specifying the branch unit and what the jump mode should be, the jump instructions and the decoder decoding the jump instructions can also control the condition code that we're checking here with the condition matcher. So if we want to do an unconditional jump, we can just set this to the always condition, the 0 value. And in this case, the program counter will just do whatever jump we configured. But if we want to do a branch with a condition, we can set this condition code to any non-zero value to check a certain condition. For example, we can set this to this value 2 we had before, which is going to be the branch on carry operation. And if the carry flag is set, we will do a jump in this case. And if the carry flag is not set, we will not do a jump. So this all seems to be working as expected. The only thing left to do is to connect these new control signals we have to the decoder and the rest of the CPU. The jump mode, I think I want to connect to bits 4 and 5 of the functional unit opcode that the decoder produces. The condition code we send to the condition matcher, I think I want to connect to the lower 4 bits of the functional unit opcode. And then last but not least, let me connect the flags input of the condition matcher to the flags RD port of the register file, which is just going to carry the current value of the flags. Okay, I think that's the new branch unit all built up. Let's go figure out how the decoder can use this new unit, and let's define a few new instructions and make use of them in a program. We currently have 3 flavors of unconditional jumps. We have relative jumps with an immediate or a register offset, and an absolute jump with a 16-bit address read from the register file. To make writing assembly a bit easier, I think I want to rename these branch instructions. All of these jumps have bits 4 through 7, where usually the RD operand would be, set to a 0. Now let's add a conditional flavor of these. Let me call the conditional operation a branch, and we'll just put the condition code into these bits 4 through 7. So whenever we want to do an unconditional jump, we can just use the jump instructions, which have the condition code set to 0. And when we want to do a conditional branch, we can use the B instruction, the branch instruction, with the additional condition code that we want to check for. While I have this file open, let me scroll down to the fswap operation. After the last episode, I noticed that now that we have precise control over when we read or write the registers and the flags, we can have a few more convenient flavors of the fswap operation. For example, we can have a flag read operation, which just reads the flags and writes the RD operand. And we can have a flag write operation, which just reads the RD operand and then writes that value into the flags. And these 2 instructions might be a bit more of a convenient way to deal with the flags, because they behave much more like a regular move operation. Let's switch over to the decoder and actually implement the decoding of these new instructions. First of all, we no longer have this program counter mode connected to the decoder ROM directly. This is now a separate functional unit. So we'll add the branch unit to the list of functional units. We have assigned that the index 2. And the program counter mode is no longer directly the program counter mode, but it is now the branch operation that we send to the branch unit. And because we're using NOR gates, the bits for these different modes have actually inverted. We also need to shift these branch operations up to bits 4 and 5 because the lower 4 bits are occupied by the condition code. And then let's make use of this new branch unit. First, let's deal with this jump with a register offset. We no longer can set the PC mode directly here. Instead, we'll have to throw this instruction at the new branch unit and set the operation of the branch unit to a relative jump. And the same is true for the absolute jump. Now, the only significant difference between an unconditional jump instruction and a conditional branch instruction is the condition code, which we've encoded in this function 2 field, bits 4 through 7. This allows us to handle the 2 instructions almost identically here in the decoder. We can just take the function 2 field and interpret it as the condition code and mix this into the functional unit operation. This will place the condition code in the lower 4 bits where we've hooked up our condition matcher, and then the upper bits will be set to the correct jump mode. This now also means that we don't just match instructions where the function 2 field is 0, which was the unconditional case, but any instruction where the function 2 field is not equal to 1. 1 was the never condition, so that would just be a no-op. We also need to indicate that the branch operations, where the condition code is non-zero, need to read the flags, because they look at the flags and then check if a condition holds. I think that's all we need for these instructions. Let's do a similar thing for the relative jump with an immediate, which we've renamed to just the jump operation. All the way at the end of the decode function, we're dealing with illegal instructions, that is, instructions that we don't recognize. This reserved jump that we've used here now also needs to go through the branch unit. And while we're down here, we no longer have this PC field that we need to pack up. And then let's go and quickly also add this flags read and flags write instruction. These are unary ALU operations, so they fit right in up here. The flags read instruction just reads the flags, but it then also needs to indicate that it just writes the RD operand. So we'll need to add a new argument to this helper function. And then the flags write instruction is the opposite. It writes the flags and it needs to indicate that it just reads the RD operand. Then let's tweak this helper function and add an RD mode operand. I think that's all we need to do in the decoder. Let me rerun the decoder script, which will recompute the data we need to store in the decoder ROMs. So we have new instructions in the instruction set architecture, and the decoder is updated to recognize them. I think it's time to update the assembler to make sure that we actually can use the instructions in the program. Let me rename the jump instructions and then add new branch instructions with the different condition codes they can have. And we also have this new flag read and flag write instruction. Let me run this through the assembler and let's see what breaks. Okay, first up we need to rename the old jump instructions. Looks like those jumps now work, and we're now failing on this new branch instruction. Let me go add that. First, we need to be able to parse these instructions, and they're going to work in a similar way to the conditional move and conditional load immediate instructions. The branches now seem to work, and we're now failing on a flag read instruction. Let me add these two new flag instructions. I should also define them as an opcode. And the parsing seems to work now for all the new instructions. And we're now failing at the encoding of instructions. Let me first make sure that we can print the new instructions back out. I'm going to factor out this printing of the target address for relative jumps, because we'll need those for the branch instructions as well. And then we can just print the new instructions. And then, last but not least, let's encode these new instructions. We need to be able to encode the condition code in bits 4 through 7, which is a different location than where the conditional move and the conditional load immediate had their condition code. So let's create two functions to encode conditions, one for the bits 4 through 7 and one for the bits 12 through 15. And finally, we want to encode the new flags operations. Let's see if this works. Pretty sweet, this looks like it's working perfectly. So armed with this new assembler, let's go and change the Fibonacci program that we've used in the previous episode to test our CPU. And I think we can make good use of these new branch instructions there. First up, we were using an fswap operation to clear the flags, but because this moves any garbage from the flags register into R0, we had to then re-clear register R0. And this would be a good candidate to just use a flags write operation that doesn't change the register R0. And then down here is the loop that we've been using to compute the Fibonacci numbers. We've had to use quite a few move instructions here, just to make sure that the larger Fibonacci number is always in R3, R2, and the smaller one is always in R1, R0. And then down here we used a conditional load immediate on carry as a kind of makeshift conditional branch instruction. But now we do actually have conditional branches. We want to continue the loop if the carry flag is not set, no overflow has happened. So we can use a branch on not carry back to the beginning of the loop. This new branch instruction is a lot nicer to use. We can make use of the label support in the assembler now because we can just use a branch with a relative immediate offset. We no longer need to fiddle with a offset in a register. And this allows us to quickly check a condition and continue a loop or break out of a loop. And since we have these convenient branches now, I think we can get rid of this temporary value in register R4, R5. Instead, we can now compute two Fibonacci numbers in one loop iteration. First, we're going to take A and add it to B. This is going to update the value in B, and so B is now the largest number. And then immediately after the addition, we can check if the carry flag is set, if the addition into B overflowed. And if that happens, we just break out of the loop and jump to a dedicated label that indicates that the largest result is now in A, because B overflowed. Otherwise, we just continue and take B and add B into A, which is going to update the value in A. And if that addition overflows, we can break out of the loop as per usual and fall through to this .b label, which indicates that the addition overflowed and now the largest result that didn't overflow is in B. We no longer need this jump offset in R6. And let me load the second Fibonacci number, the 1, into variable A instead of B, just to align with how we've restructured the loop. Now we have two ways how we're going to break out of this loop. Either we reach this .b label if the largest number is in B, or we reach the .a label if the largest result is in A. It would be convenient if the largest number ended up in the same variable, so in case we reach the .b label, let's move the largest Fibonacci number from the variable B into the variable A, and then just continue to the .a label. Once we get down here to this .a label, we know that the largest number that didn't overflow is in variable A. So let's go clear all the other registers. We could just halt the processor now, as we used to do, but I think that's a bit boring. Let's instead try to actually verify that the result is correct by using some of the new instructions that we have. For example, one thing we could do is we could do a pop count. We could count the number of bits that are set to a 1 in the result. This doesn't check the exact value of the result, but it's an interesting kind of checksum to see if the result makes any sense. And we can use a few branch instructions for this. Let's start with the lower byte. Let's move the lower byte into R2. And now we can use the same trick we've used in a previous episode to count the number of 1 bits in a number. We can shift them left, which is going to shift the topmost bit into the carry flag, and then use an add with carry to tally up the number of 1 bits. And we can use this new add with carry and immediate instruction for this. We could now copy paste these two instructions 8 times for each of the bits in this register, but I think that's a little bit boring. Instead, we can check the flags immediately here after the shift. If the shift produced a 0 value, has shifted out all the 1 bits, the 0 flag is going to be set, and we can use that to break out of a loop. We can't do the checking down here after the add with carry, because the add with carry will itself change the flags. So we need to come up with a way to have a branch instruction immediately after the shift left instruction. The best way I can come up with is to duplicate these two lines and then create a loop around the inner two instructions. Let's do the exact same thing for the upper byte, which should leave us with the total number of 1 bits in the result in register R3. If we check the expected value, 46,368, that value has 6 bits set to a 1. So after the pop count, we expect register R3 to be 6. So either there were 6 bits and we're just going to jump to this pop count OK, or we're going to fall through into this error handler, which then freezes the CPU and we see an error code in the register R6. And if all was well, we can just clear the value in R3 again back to 0 because we no longer need that result. Pretty nice. That's already a few of the new instructions tested. Now that we know that we have the correct number of 1 bits set in the result, I think we could do a bit more of a careful check to make sure that the correct 1s and 0s are set. We can again do this separately for the lower and the upper byte. We first move the value into R2, and then let's use an XOR with immediate, which we haven't used yet, to negate the value and AND it with a bit mask that indicates which bits should be a 1. If that is non-zero, the check fails. Otherwise, we grab a fresh copy of the lower byte and AND it with the inverted mask to check for the zeros. And then again, if that happens to be non-zero, we go to this fail case. And we do this for both the bytes. And then once we arrive down here, none of the branches to the failure case happened, and we know that all the bits are correct. Let's jump to an OK label in this case. In case one of the bit checks failed, let's just load an error code into R6 and halt the processor. And otherwise, if everything was okay, let's load the value 1 into R6 to indicate success, and then halt the processor as well. And so if the program stops and the processor halts, we can check the value in R6 to know whether an error happened or we were successful. Let me run this through the assembler. This looks pretty promising. I think it's time to give this a try on the CPU. First, let me program the updated decoder ROMs. Let me start with the first decoder. Then the second decoder. And then finally, let's update the program memory. Okay, let's power this up and see if it works. All right, this looks pretty familiar. So first we're loading a 0 into register R0. We're then moving the 0 value in register R0 into register R1 and into all the other registers. Pretty nice, that still works, and the register file is cleared. And now we're already executing a new instruction. This is a flag write. We are taking the value in R0 and writing it into the flags register. But unlike a flag swap, we're not taking the flags value and storing it back into R0. So this is a one-way exchange between the register file and the flags register. The decoder still selects the ALU as the functional unit and it executes an fswap operation. But for this flags write, we're only reading from the RD operand. We're not writing back to the RD operand. Then we're not doing anything with the RS operand. And then the flags, we are only writing and not reading. This is different from a flag swap where we would do a read and the write of the RD register and the read and the write of the flags register. And when I hit the clock, we're going to see the 0 in register R0 be copied into the flags register, which is exactly what happens. Pretty neat. And now we're entering the loop to compute the largest 16-bit Fibonacci number. We're starting out by setting R0 to the value 1. This now means that register R1, R0, the 16-bit value here contains the second Fibonacci number, which is the value 1. And the register R3, R2 contains the first Fibonacci number, which is the value 0. Compared to the previous episodes, we now have a more efficient loop to compute the Fibonacci numbers. Instead of doing a lot of moves, we're mainly just adding things back and forth between two registers. So in the first step, we're adding register R1, R0 into register R3, R2 with two add operations. The first one is a regular add, and the second one is an add with carry to create a 16-bit addition. And yeah, that worked. We have computed the next Fibonacci number in register R3, R2 down here. This is the value 1. And now here comes the star of today's show. This is a conditional branch operation. The lowest 4 bits are the value 9, which indicates either a jump with an immediate offset or a conditional branch with an immediate offset. And then the next 4 bits, not being 0, indicates that this is a conditional branch. And this is a branch with carry, so in case the previous addition overflowed, we would now branch and break out of the loop. The decoder does its thing. It indicates that we're not using the RD operand. We're using an 8-bit immediate, which is the jump offset. And we're reading the flags because this is a conditional branch, but we're not changing the value in the flags register. And then the second decoder ROM now selects functional unit 2 to execute this instruction, which is the branch unit. And correspondingly, you can see that the branch unit enable LED goes on. The topmost 2 bits of the opcode indicate that we want to do a relative jump. The lower 4 bits of the opcode indicate the condition under which we want to do this jump. And this is the carry condition. And since the carry flag is not set, the condition match circuit here indicates that the condition does not match. And then correspondingly, the branch unit, instead of forwarding this relative jump that we're instructing right here to the program counter, it just keeps the program counter in normal stepping mode. And so instead of jumping forward in the program a bit, we're going to see the program counter just count up by the value 2, as if this jump were a NOP instruction. And indeed, we didn't execute the jump, we just stepped to the next instruction. And the next instruction in the program is another add. This time we're doing it the other way around. We're taking the value R3, R2, and we're adding that into R1, R0. That again worked, and it did not produce any carry flag because the numbers are still pretty small. Now we're doing another branch, but this time it's a branch on not carry. Basically what we want to do is if the carry flag is not set, if there's still more Fibonacci numbers to be computed, and indeed the decoder selects the not carry condition, which is forwarded to the condition matcher. And since the condition matches, this relative jump that the decoder is asking the branch unit to do is being forwarded by the branch unit to the program counter. And when I hit the clock, the program counter is now going to jump back to address hex 12, which is the beginning of the loop. And that's exactly what happened. So we had 2 conditional branch instructions. The first one was a branch on carry, which we did not execute because the carry flag was not set. And the second one was a branch on not carry, which we did execute because the carry flag also wasn't set. This is pretty exciting. This looks like it might just be working. Let me hit run to skip over the first part of this program because we're computing Fibonacci numbers and we need quite a few iterations to do so. Let me step through the remaining instructions until we create an overflow in computing the Fibonacci number. And indeed, the previous value we had in R3, R2 here was the value 46,368, the largest 16-bit Fibonacci number. And after the addition of this value into register R1, R0, the carry flag is now set, and basically this is the result of this overflowing addition. And so we're now back at this branch on not carry instruction that would try to continue the loop, but in this case, because the carry flag is set, the condition match circuit tells the branch unit that the not carry condition doesn't match in this case. In fact, the carry is set. And so instead of jumping back to the beginning of the loop and continuing, we're going to break out of the loop now. Pretty nice. That takes us to address hex 1e, which is the done B label of the program we had. So now we're moving the value from R3, R2 into R1, R0 to make sure that at the end of the loop, the result is always going to be in R1, R0, which works, and we're going to zero the other registers. In our previous versions of the program, this is where we would stop. We've computed the largest Fibonacci number, and that was good enough. But we've since updated the program to now actually go in and check the result if it makes sense. And so in the first step, we're going to now count the number of 1 bits that are set in this 16-bit value. This should come out as the value 6 because there are 6 bits set. So we're first going to count the number of 1 bits in register R0. So we're copying that into register R2. And now we're doing a sequence of shift lefts and add with carries to tally up the 1 bits. First up, we're doing a shift left logical. We haven't seen that yet with the new decoder. So this selects the ALU as a functional unit with the shift left operation. And in fact, that shifted the 0 out at the top and into the carry flag. And now we're using an add with carry and immediate operation to take the carry flag that might be set right now and add it into register R3. We haven't seen this instruction yet with the new decoder, but it's actually pretty simple. It selects the ALU and add with carry mode, but the RS operand is set to the 4-bit immediate mode instead of a register mode. So that doesn't do anything because the carry flag was 0. Now we're doing another shift left. And now we've reached the branch instruction that is now going to continue this loop of shifting left and then adding with carry. This is a branch on non-zero because we want to keep shifting left until there are no more bits left in the register, and we've seen all the ones and tallied them up. And since the register is non-zero, the 0 flag is cleared. And so when I hit the clock, we're jumping back to the beginning of this very small loop. Now, since the previous shift has moved the topmost bit into the carry flag, we're now calling the add with carry instruction here to tally up the number of 1 bits. But the carry flag is 0, so this doesn't do anything. And now we're doing yet another left shift. This now has shifted the 1 bit that was at the top out of the register and into the carry flag. And because the register is now 0, the 0 flag is also set. So in this case, the branch on non-zero instruction does not see its condition match. And so when I hit the clock, we're breaking out of the loop. And at the end of the loop, we have yet another add with carry and immediate instruction because the shift left might have shifted something out into the carry flag, which is the case here, which we still need to tally up. That worked like a charm. Register R0 has a single bit set, and correspondingly, R3 contains the number 1. Now we're going to do the same thing with the upper 8 bits. First, we copy them into register R2. And then we're doing the same sequence of left shifts and adds with carry. All right, we have shifted out the last bit now. And again, the branch on not 0 is not going to be taken because the condition no longer matches because the value has reached 0. And we're breaking out of the loop. And then we're doing the last add with carry to tally up the final bit. And that leaves register R3 with the value 6 in it, which is indeed the number of 1 bits, the pop count of the value in R1, R0. But our program now wants to check this, so we're doing a compare with immediate of the value in register R3. And this is also an instruction we haven't seen executed yet with the new decoder. And in fact, this works pretty much like a regular compare operation. The ALU is selected in subtract mode, but we're only reading the RD operand, we're not writing back to it. So the result of the subtraction never lands in a register. And the RS mode is set to 4-bit immediate because we're comparing with an immediate, and then we're updating the flags with the result of this operation. And since the 6 that is in the register matches the 6 we pass as an immediate to the compare instruction, this will evaluate to a 0 value, which is our indicator that two values are equivalent after a comparison. And now we're doing a branch on equal. And after this instruction in the program, we have a few instructions that set some error code in the register file and halt, such that when this value here wouldn't be 6 if the comparison didn't yield an equal result, we would actually set the value in a register and then halt the processor to show that something went wrong. Pretty nice, our processor is now at the Popcount OK label. So we're now clearing R3 back to 0. And now we're checking that the actual exact values in the registers are correct. We're doing it in a somewhat cumbersome way to test a few more instructions. First, we're checking the lower 8 bits, so we're copying those down into R2. And now we're first checking if the correct bits are set to a 1. We're first inverting the value in R2 here with an XOR with the immediate instruction, with the immediate set to -1. And what this does, -1 as a 4-bit value, is all bits set. And in 4-bit immediate mode, we're sign extending this to a full -1 in 8 bits, which is all bits set. And when I hit the clock, the bits in R2 flip. Now we're using an AND with immediate operation to take the value in R2 and AND it with a bit mask of all the bits we expect to be a 1. This will leave the register as a 0 if all the correct bits were set, or a non-zero value if some 1 bits were missing. Pretty nice, that leaves register R2 as the value 0, which means all the correct bits were set. Since all is well and this was 0, the 0 flag is set, the non-zero condition does not match, and we're not taking this branch. The branch unit is just going to instruct the program counter to step to the next instruction. The next instruction checks the 0 bits in the value, so again we're copying R0 down into R2. And then we're doing another AND immediate, this time with the inverted bit mask to check that all the other bits in the number are actually 0. And again, we're doing a branch if non-zero to an error handler, but since the condition doesn't match, everything checks out, we're not taking the branch. Instead, we're doing the same check now for the upper 8 bits of the result. Alright, so we've reached a point in the program after this bit checking, and none of the bit checks have failed, so we haven't jumped to the error handler. We're now doing an unconditional jump, which isn't totally necessary, but this is now jumping over that error handler, and it's a good opportunity to test the regular jumps still work. And in fact, you can see the 9 down here indicates that this is a jump or branch instruction, but the next 4 bits are a 0, so technically this is still a conditional branch, but since we're picking the always condition, and so we've labeled this an unconditional jump in the instruction set architecture. So we're now jumping over the error handler, and we're now at the location that in the program we called the bitcheck OK label. All this now does is it loads the immediate value 1 into register R6 to indicate that the Fibonacci number computation was successful. And then finally, we have a halt instruction, which just halts the processor. This is really exciting. It looks like the conditional branches work pretty much out of the box, and it didn't really need a lot of changes to the circuitry, just a small little helper PCB to evaluate condition codes and a NOR gate chip down here. And I can now reset the processor and hit run, and it just computes the largest 16-bit Fibonacci number, and then also checks that the result is correct and sets this 1-bit down here in register R6. Pretty cool. I'm actually kind of curious right now how fast the CPU might run with this current clock generator. It uses this capacitor over here to slow down the oscillation of the 555 timer to a reasonable level, Well, I can rip that out, and then the 555 timer's oscillation should only be limited by the capacitance of its own pins and the PCB traces. So let me hit run such that the clock is ticking and hit reset to restart the program. So it looks like the program is executing almost instantly. Whenever I hold reset, the CPU goes into reset state, and you can see the registers aren't doing anything. But then as soon as I let go, the program executes and finishes almost instantly. This is pretty exciting. I'm not sure how fast this is going to run. I don't think this is going to be more than a few kilohertz because the 555 timer is fairly slow, especially in the configuration we have it right here. In a future video, we'll take a closer look at where the critical paths are in the CPU and how you can model and compute the speed at which your CPU will run. As a next step, I think it would be good to have a kind of output system attached to the CPU such that we can have programs that compute something and then display the result. I think I'm going to use the standard liquid crystal display that a lot of other people use to be able to display a little bit of text from the CPU. And I think the setup we have here with the decoder is going to make that pretty straightforward. But the timing requirements involved in talking to that liquid crystal display, I think are going to inform quite a few of the next step of how we need to change the CPU to make it ready for out of order execution, out of order write back of results, and then later also Superscalar execution. Because I'm pretty sure the display is going to be pretty picky about how you talk to it and when certain signals change, which is not going to be compatible necessarily with a CPU out of the box. And instead of changing the timing of the CPU to match what the liquid crystal display can accept, I think this is a great opportunity to create a small circuit to talk to the liquid crystal display and deal with the weird timing requirements. And then that would be a unit that potentially takes multiple cycles to execute a single instruction, which currently we never have encountered in the CPU. And this is going to open up a whole can of worms in how to control the CPU and how to allow a CPU to stall and react to functional units that cannot progress and accept new instructions. And essentially all of the out-of-order write-back, out-of-order issue, out-of-order execution, and superscalar execution are born out of a desire to deal with this inability to do more work and kind of skirt around the functional units that can't do work at the moment and try to fill up other functional units with work in the meantime. So I think that would be a pretty good motivation to continue on with this build, and it's also going to provide a pretty fancy way of outputting things in textual form, such that when we compute things like a Fibonacci sequence, we don't need to stare at registers and figure out what the binary patterns mean. We can just look at the liquid crystal display. That's something for the future though. Thanks a lot for watching, like and subscribe if you want to see more of this, and see you next time.